Okay, students, welcome to the last part. Part 3. We're going to look at the squeezing theorem. Kind of an interesting way to look at certain types of limits. And then we're going to finish it off with a little talk about how limits relate to relativity theory by Albert Einstein. So hopefully that'll be interesting to you. So the squeezing theorem basically says if you have three functions and there's one in the middle kind of squeezed between these two, so you have this kind of function here, h of x, the one on top, you have f of x, the one on bottom, but then you've got this squeezed in the middle, g of x, and what it's saying is in a real small neighborhood around a, if all of the function values on f of x are less than or equal to g of x and less than or equal to h of x in this small neighborhood, then the squeezing theorem basically is going to say that you can do the limit of f of x, the limit of h of x, and if they're the same, then the limit of g of x will also be the same as well. So reading the squeezing theorem, it says, assume the functions f, g, and h satisfy the inequality. F of x is less than or equal to g of x is less than or equal to h of x for all values x near a except possibly at a. Then the theorem says if the limit of f of x as x approaches a is equal to the limit of h of x as x approaches a, if they're both equal to L, then we conclude that the function that's squeezed or sandwiched in the middle must have the same value. So notice that they're both equal to L. All right, so kind of think of yourself as you're in public transportation and you are squeezed between two people, or you're on an airport. All right, so you can kind of think of the squeezing theorem that way. You can think of the sandwich theorem, it is often called. All right, so on the next page, I'll show you how to do this, and these are pretty simple to do. What we're going to look at in the squeezing theorem is given an inequality. So I'm not going to go through showing that this is true, but you have the function 1 minus x squared over 6 is less than or equal to sine of x over x less than or equal to 1. Okay, so this is true whenever x is near 0. So what we're going to do on this is we're going to end up finding the limit of the function that's in the middle of the two. All right, so you kind of have three functions, 1, 2, 3. What you're going to end up doing is you're going to try to find the limit of the first and third, and if they are equal, then that will be the value of the limit of the function in the middle. So graphically, one thing that's kind of an interesting thing to do on the squeezing theorem is just to look at this on your graphing calculator. So I went ahead and provided you the graph. So go ahead and put this in your calculator. In y1, put the first function, 1 minus x squared over 6. In the y2, put in the function in the middle, sine x over x, which is kind of a famous limit that we're going to look at a little later. And then finally, we'll put in 1. So we're going to look at, on the graphing calculator, let's just set a window up going kind of like I have down here, -5 to 5 by a scale of 1. And let's make the y's go -2 to 2 by a scale of 1. So let's use that as the viewing window. And when we graph this, you're going to see these functions kind of like this. Now, they're all squeezed together. The one in red is the one we're interested in. That's the graph of sine x over x. So it's sandwiched. Its function values are always under the function 1, and they always seem to be above the parabola 1 minus x squared over 6. So you're sandwiched in the middle. If you want to label these, you can. This one is, we just have, we'll call this f of x. Let's do this kind of like this. So f of x is the one in the middle. and then that's equal to the sine x over x. If you want to label this, you can. Then let's see, G is going to be, hold on, let's do it like this, just to be kind of consistent with the way the theorem says. So let's call this one f of x here. Let's call this one g of x. And then let's call that h of x. Doesn't really matter which order you do those in. So what we're saying is that f of x is less than or equal to g of x is less than or equal to h of x on this small neighborhood right here. So by the squeezing theorem, what we're going to do is you just kind of show your steps like this. What you do is you do the limit x goes to 0 of the first function. All right, now all you got to do on this is just plug in the 0. This is like a polynomial function, so you get 1 minus 0 squared over 6. That's 1 minus 0 over 6. That's 1 minus 0, so that's equal to 1. So we do that. Now the next thing we do is we're going to do the limit of the third function. So we do the limit as x goes to 0 of 1. Well, the limit of a constant's always equal to that value, so that's also equal to 1. So what I want you to notice is they both turned out to have exactly the same function value, so we can now conclude, we just say, therefore, the limit of the function in the middle is also going to be equal to 1. All right, so that's what you have to do. You have to show, I give you the inequality. You do the limit of the first function and the last function. If they turn out to be the same, then the limit of the function in the middle will turn out to be the same also. So that's how you show that. And you can pretty well tell on your graphing calculator that they're all coming in towards y equals 1. The left and right hand limits on every one of these functions is all squeezing in to y equals 1. So that's the idea of the squeezing theorem. All right, so pause if you need to pause. Otherwise, go to the try this problem, and I'll let you all work on this one. Try to show the steps the same way I did. I'm giving you this inequality. You're going to find the limit of the one in the middle. So just do the limit of the first and third. If they're the same, then you conclude that the limit of the function in the middle is also the same. Okay, so just want to make sure you know how to show your steps correctly on this. Okay, so the answer is 1. So basically here's the idea. This is what you always want to consider in the problem. I've given you an inequality where you have you have 3 functions, and one of them is squeezed in the middle of the other 2. So what you want to do is you want to do the limit of 1 plus x cubed as x goes to 0. It's a polynomial, plug in 0. 1 plus 0 cubed would be 1. Okay, do the limit of the third function. Same thing happens. You get 1. And since they're equal, then you can conclude that the limit of the function sandwiched in the middle as x goes to 0 is also to 1. And then you do need to state by the squeezing theorem. So you're doing a proof, kind of a simple proof on that. And the graph I gave you, you could graph each of these 3 functions on your calculator if you wanted to. But the idea is they're all going towards y equals 1. You can see they're all heading, when x is 0, they're all coming to that same point like that. All right, so that's how the squeezing theorem works. The next thing I'm going to do on the next page is just a little discussion of relativity. The first thing that I want to do is show you this video and let you watch this video. This video will help you, I think, understand the relativity concept a little bit better, hopefully. Okay.
ADHD
all right.
10 hours
so we got an ad here.
But no, by all means.
Let me skip that ad. Okay, so watch this.
Again. Let's talk about length contraction.
He knows a lot about the science stuff. Professor Dave explains.
Einstein's special relativity was a huge step in physics. And even though time dilation seems like the weirdest thing you've ever heard, there's plenty more to get through with this theory. As it happens, it's not just time that's relative, it's length as well. And as we will find out, the math tells us that when you approach the speed of light, your measurement of space changes just like time. This is because if an observer on Earth and an observer in a fast spaceship register different spans of time for an event, they must also be recording different distances, since both observers agree on the same relative velocity between them. Specifically, the faster you go, the smaller objects seem to be, and the shorter the distance you perceive yourself to be traveling. This is a phenomenon called length contraction. Here we can see two versions of a spaceship traveling very fast to a faraway celestial object. In one, we see things from the perspective of an observer on Earth, and in the other, we see things from the perspective of someone on board the spaceship. The Earthbound observer sees the spaceship moving at some velocity v, notices time moving at the familiar rate, and can measure some distance for the journey, which we label as L0 and refer to as the proper length, as this is the length that is measured by an observer that is at rest with respect to the objects demarcating the distance. But on the spaceship, the only thing that is the same is the relative velocity v, though in this case it represents the velocity of Earth and the destination as they move relative to the ship. And because this velocity must be the same as for the Earthbound observer, everything else must be different. Because of time dilation, the time interval will be different, delta t0 rather than delta t, and we label the contracted length of the journey as L. The relationship between L0 and L is given by this equation, which can be derived from the time dilation equation. Not only do the two observers arrive at different values for the length of the journey, they even arrive at different values for the length of the spaceship, as this dimension is parallel to the direction of travel. The Earthbound observer would see the ship as being much shorter than the astronaut does. In fact, this discrepancy in length neatly explains how the two observers could perceive different rates for the passage of time. It also explains how fast-moving particles can defy certain expectations, because at such speeds, time slows down, and the distance traveled contracts. So, a particle like a muon, with a half-life of a millionth of a second at rest, is able to exist for longer and travel further than expected when moving near the speed of light, due to relativistic effects. At this point, let's take a moment to make sure we understand how to assign delta t and L values. Delta t0 is the proper time interval, which is the time interval as measured by the inertial reference frame where the two events occur in the same location. For a space journey, that's the spaceship, because the Earth leaves and the destination arrives while the ship goes nowhere. Everyone else, like someone on Earth, will register a longer time interval, delta t, for this journey. L0, the proper length, however, is length as measured by an observer that is at rest with respect to the objects in question, like the Earthbound observer is in this case. Anyone in motion with respect to the objects, like the person on the spaceship, will register some shorter length for this distance, L. This means that the proper time and length may not always be measured by the same observer, and we need to know how to assign these in order to do the math correctly. Let's say a ship is traveling from Earth to another system at 90% light speed. The person on board measures the journey as being 8.2 light years in length. How far away is the destination according to someone on Earth? Well, we can plug in 8.2 for L and 0.9 c for v. Then we just do some algebra and we should get 18.8 for L0, or the proper length between Earth and the destination. We still have more to go with special relativity, but first, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Thank you, Professor Dave. All right, so I'm going to go back to OneNote, and I'm going to give you an example of one of these things. So relativity is very bizarre, and it's just something that we don't see in our day-to-day existence because we're not traveling near the speed of light. And when you start getting close to the speed of light, things change. So let me show you how this works on this, and this is pretty straightforward. This, again, is the Lorentz contraction formula that you saw on the video. And c is the speed of light. L is the spaceship's length. Okay, and the spaceship is traveling at a speed v relative to an observer. So to the observer, the ship appears to have a smaller length that given by this formula. So the length is going to appear to contract. So I'm going to just go through these questions here. What is the observed length L of the ship if it is traveling 50% the speed of light? So what we're going to do on this is we're just going to let V be 50% of C. C is the speed of light. So V is going to be 0.50 C, or just 0.5 C. Now what we're going to do is we're going to replace this value in for V like that. Now, let me show you what happens then. So what we'll get is we'll get L equals L naught times the square root of 1 minus 0.5, and you have to square that, so you have to be kind of careful on how you write this. So this will be 0.5 C squared over C squared. Okay, so that's going to be L naught, and we get 1 minus, if you square 0.5, that is 0.25 C squared over C squared. Now what's going to happen is these are going to go away. Those divide out. So you get L naught square root of 1 minus 0.25. So you end up getting L naught times the square root of 0.75, like that. Now, if I take the calculator on this, this will go like this. So I'm just going to take the square root of 0.75. So that's about, we end up getting about 0.87 L naught. So the conclusion we get on this is it appears that it contracted by 0.87. So you've got this original length like this, and that is the observer, okay? So the speed on the spaceship, it looks like their distance has contracted by 0.87. So that is the result that we get on that then. So it's contracted. Okay, let's see what happens if you're 75% the speed of light. So we do this the same way. We say V is equal to 75% of C. So that would be, in other words, 0.75 C. And again, we're going to substitute in for V squared this 0.75 C. So L is equal to L naught times the square root of 1 minus, now replace V with 0.75 C, then square it, and divide by C squared. So I'm just plugging this value into the Lorentz contraction formula. Okay, now we're going to work this out. So we have L naught, and we'll need to use the calculator on this, see what we get. So we're going to take 0.75 squared, and that's going to give this amount. So we get 1 minus 0.5625 C squared over C squared. And what happens is that divides out. So we're going to end up getting L naught times the square root of 1 minus 0.5625. And then we'll go ahead and do that. I'll just do that. I'm just going to do it on one step on the calculator. So square root of 1 minus 0.5625 is going to give you this value then. So this is about L naught times, and let's just write this like this. So it's approximately 0.66 L naught. So it's contracted further. So if you look at these results right here, the second result is L is approximately 0.66 L naught. So if you look at these values, it's contracted more. All right, so what ends up happening on that is you're contracting more and more as you get closer to the speed of light. All right, so that's how that works out. Okay, so see, this number is getting smaller right there. So you're going to end up, if we went to like 90% the speed of light, you would see this number get smaller and smaller. So it's contracting by a value. So let me just give you an example. So say, for instance, that we know the observer at rest, the spaceship it's like 2 meters long or something. So if we take 0.87 times 2, we get this. 0.66 times 2 gives that. So what's going to happen is it's just going to get shorter and shorter and shorter as the speed of light, as we get closer to the speed of light. Okay, so the idea on this is L appears to get smaller. Okay, so now we're going to do a limit. We're going to apply this to calculus. So what we're going to do on this is we're going to look at the limit as V approaches C from the left. Now, in relativity theory, you cannot travel faster than the speed of light. That's why we have to have a left-hand limit. All right, so what we're going to do is just going to plug in. So we're just going to take that C and plug it in. And let me show you what happens. So we get L naught, then we get the square root of 1 minus C squared over C squared. So that would be L naught. That would be 1 minus C squared over C squared. That divides out. So you're going to get L naught times the square root of 1 minus 1. So that's L naught times 0. So what's happening is we're going to 0. All right, so as we get closer and closer to the speed of light from the left-hand side, that limit approaches 0. So it looks like the length contracts to 0. All right, that's kind of interesting, and relativity is a very fascinating subject worth exploring. All right, hope you enjoyed the video, and basically the squeezing theorem is what you want to know, and I thought I'd just give you this example because I think it's kind of interesting. Hope you did too. All right, have a great day.